Yes. So it's a math talk, as you see. It's on the blackboard to show that it's pure math. A little bit different from the majority of the conference. And so the main point is that the fractional, well, in the fractional quantum Hall effect, there are these Laughlin states. Laughlin states are holomorphic sections of a holomorphic diagram. I will explain that. And that makes it possible to study them with methods of algebraic geometry that are usually not used in physics. So I have a problem with this topic. I have to explain methods to which people are not necessarily used. But this is the main novelty, the main interest of this thing.
So you want to say it's the first time methods of algebraic geometry used in real
I don't know if it's the very first time, but I think the Grothendieck-Riemann-Roch formula, maybe I think it's the first time it's used for the quantum Hall effects. It allows to prove some things that were kind of known to physicists without a rigorous proof. Okay, so it is not possible to really study, well, to really make a closed surface with a transversal magnetic field. So maybe in practice an experiment will look like that. This is the conducting plate. So you shouldn't take this picture too seriously. It's the way a pure mathematician imagines an experimental setup. Okay, the important part is that usually when you do quantum Hall effect, you have a rectangle, and then the Hall conductance is just a number. You measure the current in the x direction, the difference of potentials in the y direction, and you get, well, you divide one by the other, and you get one number. But here, there are, you see, 4 measuring devices that corresponds to a basis in cohomology of the surface. So this surface will be called C. So it has a basis with A cycles, maybe I can call them A1, AG, and B1, BG. A symplectic basis. And
what is CR?
C, so C is this surface. C is the surface. R are real numbers. So cohomology with coefficients in R.
Which, sorry?
Real numbers.
No, I understand, but what does that corresponds to?
Why real numbers? Just because the current and the difference of potentials are real numbers.
Aronoff-Bohm fluxes of the holes.
This is R.
Aronoff, yeah.
So where it will.
C is the surface.
C is the surface.
C is the surface, yes. So in this case, we have instead of x and y, we have x1, x2, y1, y2, and the whole conductance. It's actually a two-form because it's a two-form. You can measure the current along one of the devices and the difference in potential with another device, and for any 2 devices you get a number. So it's actually a two-form, and it will turn out, so you will, that's part of the answer, it's some constant that we will determine times some dxi dyi for I from 1 to g. So for genus 1, if you are on a rectangle for genus 1, you just get one number, this constant times dx dy. But in general, it could be.
To be pedantic, is it like a slower one? What we have in mind there?
So this is I mean, they are identified by the Poincare duality, so it's really not. I mean, I thought about it. There's not really a natural answer sometimes.
One more comment on notation. If you want to be pedantic, it's not conductor, it's a semiconductor. It's
actually.
Oh, this one, okay.
It's like
okay.
This I accept immediately. I'm not a physicist, so if you say so.
At R, it's okay. But once you insist on R, then please.
So in the ordinary quantum hole, what are x1, x2, y1, and y2? Are they not just
In
two
the ordinary
parameters?
quantum hole, you have the x direction here and the y direction here.
Yes, and the 1 and the 2.
And there's just one. This is x1 and y1.
Ah, okay.
Right?
So it stops there.
Yes,
Okay.
that's because we're in genus 1. And in genus 2, there's x1, x2, and y1, y2. And this makes the problem more interesting. Okay, so let's start with one particle.
So Dimitri,
Yes.
just maybe to clarify, so x and y, they have nothing to do with space. You know, the flux is through the... It's not real space, that's why you have more coordinates. It's a Jacobian of your...
They are, so they are, okay, so we will come to that, but the Jacobian is the factor of r to the power 2g by a lattice, and these are the coordinates in this r to the power 2g.
Should I think of them as the fluxes I can insert through my...
No, these are... Yes, yeah, so this is the space of fluxes, yes. But, so I don't know, you see this is the space that is unique, but you can interpret it in different ways. You can measure a current, or you can measure difference of potentials or a flux, and each of them takes values in this space. So it's both the space of fluxes, but when we measure a current along one of these cycles.
Or maybe the fluxes are supposed to be on the circle, not on R.
So, okay, so it's what happens when you add a flux? Right? You switch on the electric field. We will come to it. We switch on the electric field, and then the flux changes. Right? It does not go. It can change indefinitely. It doesn't go back to the same place. It's just that at some point you get well, when it becomes integer, you get a connection that is gauge isomorphic, gauge equivalent to the original one. So you can factor by a lattice and obtain the flux space that is compact, that is a torus. Right? But in principle, you don't have to do that. You could take a real space. That's
You agree that this is flux, the space of flux?
yeah, this is the same. So it's not a question issue. It's you see, mathematically it is the space, and then it has different physical interpretations.
Physically, this equality there refers to one rather than the other. The equality with the exclamation point.
Yes.
That refers to one interpretation rather than the other. That the space
Yes,
is
so-
a space of fluxes.
Yeah, and yes. Let me do my example with one particle. So when we have one particle on this surface, the wave function is an L2 section, so square integrable section of a Hermitian line bundle. And the magnetic field is a connection. The magnetic potential, right? The magnetic potential. Yes.
connections of the.
So these two, so once we have a connection on a Hermitian line bundle, this immediately defines the operator d bar, which is the 0-1 part of the connection. And so Hermitian line bundle, let me call this L, and so L becomes holomorphic. And then the ground states are holomorphic sections of L.
So the ground state of whom? Of which operator?
The ground states of the one particle Hamiltonian, and actually it has to be fine-tuned a little bit. It is not always like that, but to get a nice theory, we take a Hamiltonian that was that is proportional to the Laplacian of this d-bar operator, and then the ground states are holomorphic sections.
Mm-hmm.
Okay, so now.
Sorry, very simple question. What do you assume about the magnetic field exactly? Is it allowed to vanish, or is it?
So the magnetic field, so this is a question of how to fine-tune the Hamiltonian. You can imagine that the magnetic field is constant, meaning that it's the same flux per unit of area on the surface.
But, I mean, it doesn't have to be. So how much can I relax this?
No, it has to be, well, it has to, so when you write the Hamiltonian, there is a term with the magnetic field and there is a term with the curvature of the surface. And then it depends a little bit on the properties of the semiconductor. There are coefficients, but there is one thing that must cancel each other. Either the magnetic field cancels the curvature or the coefficient that involves the curvature is small, and then the magnetic field should be constant. But it cannot be arbitrary. It cannot vary arbitrarily.
And there is the shift when you have curvature, right? The Gauss curvature plays the same.
Zero. Yeah, the Hamiltonian is this term is zero. Curvature.
I think the question was
Yes.
in anticipation that cohomological characteristics like Hall conductance depends on the net magnetic field, to the total flux going through
The total flux will appear in a second. Yes.
Not on local distribution. Is this right?
No, but for
Magnetic field could be non-uniform, but on the total flux.
For this thing to be true, you need the magnetic field to be uniform or to compensate the curvature.
Yes.
For this thing to be true. So this is something that's.
No, but
I think.
No, you can have curved surface and constant magnetic field.
Yeah.
But you can relax magnetic field, make it not constant, and
you have to just
zero mode remains.
If in the Hamiltonian this term somehow is zero, the coefficient is tuned to zero, then yes, then you don't even need that. But generically, having curved surface is not a problem if magnetic band is constant.
People always.
But again, it's not a question for me. So for me this is the condition that has to be satisfied in some way, and then the physicists or engineers decide what is the.
No. You should not mention anything about physics. This is
No, I have to. If I have to be understood, I have to translate a little bit. Okay. So now we have the first example where the formula from algebraic geometry can answer a physical question. The physical question is, what is the degeneracy of the ground state? Right? Degeneracy of ground state.
good.
And this is, in mathematical notation, this is the dimension of the space of sections of this holomorphic line bundle L. So here we have a Riemann surface, a holomorphic line bundle, this thing denotes the dimension of the space of holomorphic sections. And there's the Riemann-Roch formula. That tells you that this H0 minus H1, on which I will comment in a moment, is equal to the degree of L, which is the total magnetic flux. Total magnetic flux. Plus 1 minus G. So we almost have an answer. There is this annoying term, but actually H1 is equal to 0 if the degree of L is greater than or equal to 2G minus 1. So for a physicist, this is not a very serious restriction because usually the flux is very large and the genus is something like 1 or 2. So we can remove this term and we get an answer, and notice that we don't have to write out any concrete wave functions, any sections. So Laughlin states, there are formulas for Laughlin states using theta functions. They will not appear in this talk because this formula just gives you the dimension of the dimension of the space without any need to know the particular form of the sections. Okay, so now the point of this talk is actually to enhance this formula in 3 ways. First, we need to switch on the electric field. We will have to, so we will go from 1 particle to n particles. And so Laughlin states. And we will add the name Grothendieck to the formula. Yeah, so the Grothendieck-Riemann-Roch formula is a generalization of this for vector bundles on families. Instead of 1 curve, we will have a family of family of Riemann surfaces. Okay, so let's try to do things one by one.
So may I ask a quick question before,
Yes.
while you're raising? So when you talk about Laughlin states, you mean that there will be actually fractional quantum Hall effect? Or?
Yes.
Okay.
Yes. It's still in the title, there's this F. Yeah.
When you say electric field, do you mean interaction between particles?
No, not interaction. No, just
Potential.
So these fluxes, the fluxes. So we're
Okay.
so
But then, but if it's fractional, then Riemann-Roch condition must be modified. Fraction must be entered, right?
Yes.
Which is not.
So far not. It's
They
an
have-
example.
The way it's written. It's
It's an example.
no. In this case, so for 1 particle there is no difference. For 1 particle, it's right. So Laughlin states the way the
There is no Laughlin state.
It will appear. It will appear. Just give it a second.
Let's wait for something.
Just
Let's go on.
Okay, so when we switch on the electric field, what happens is that so the electromagnetic potential, I cheated a little bit. When I said it was a connection on this line bundle, it was a little bit of cheating. Actually, it's a connection on the line bundle over the space-time. So I should take my surface C, multiply it by the time line, and take a connection on this. And this is, and then we can trivialize the line bundle along the time lines, so that what we will obtain is that this connection will change in time. when I switch on the electric field, that means this connection changes with time. So I have the same Hermitian line bundle, but the holomorphic structure changes. And so now I properly introduce the space of Aharonov-Born fluxes. So in math it's called the Picard group of the Riemann surface. So for a physicist it's the space of Aharonov-Born fluxes. For a mathematician it's the space of degree D holomorphic line bundles. Line bundles modulo isomorphism.
And what's D?
D is the degree of L. It's the total magnetic flux. Let's
Good.
down here. Total magnetic flux. Yep. So this is a torus. I think you all know this is c to the power g factored by a lattice. So it is homeomorphic to a circle S1 to the power 2g. It's a torus of real dimension 2g, yes?
So it's slightly related, but so now you introduce an electric field by making the connection time dependent.
Yes.
If you were on a plane, you could alternatively introduce an electric potential. You could gauge transform one to the other. Is that picture lost here on the Riemann surface, or?
Sorry, the electric potential, that's, I didn't mention.
Giving an electric potential.
It's a particular gauge. It's a particular gauge when you just use vector potential.
Generalized along the line,
On
right?
the
That's
plane.
when you killed that potential.
Ah, I see.
On the plane, that's equivalent, but now you couldn't do it this way. So instead of changing the connection, putting an electric potential, that's no longer equivalent.
I think they never use an electric potential. They always generate the electric field using a magnetic potential.
Yeah, but that's gauge equivalent on the
It
plane.
is equivalent. It's just they do.
But is that statement still true on the Riemann surface? Is my question.
I think it's a different gauge trace. Maybe this is.
Yeah.
I'm sure there is a simple answer, but I'm not sure I can give it right away. Okay, and and one thing. And there is a theta divisor inside here. Theta divisor. So it's a complex codimension 1 Saclay, and its Poincaré dual cohomology class is what I wrote somewhere. I think I erased. It's the sum of dxi dyi for I going from 1 to g. So we will use that a lot. Okay, I think this is the first take on the electric field. Yeah. So this is the symplectic form. So there is a symplectic form on this torus that is Poincaré dual to the theta divisor. So I will denote it by theta. Okay. So what do we do with n particles? So you all know about Laughlin states. So a Laughlin state depends on n points on the surface, and here is where the fractional part appears. So it is proportional. It has a 0 of order at least b as zi minus as two particles collide. And it is symmetric or antisymmetric. Well, usually B is odd and then it's antisymmetric. Okay.
Can I ask one question?
Yes.
In the A part?
Yes.
So, introducing a flux is equivalent to tensoring L by an element of peak 0 or something like this? Okay.
Yes. Yes.
Okay. Okay.
Yeah, and so, okay. Right, and so this is again a holomorphic section of some line bundle. So let me, okay, so first of all we can look at c to the power n, the nth power of the surface, and then we have the line bundle. We pull back L from all copies of C. So that means that psi, if you look at how psi varies in one of the i's, it's a section of L. And then if we want to impose zeros, we subtract some of the diagonals. So delta ij is the diagonal where zi is equal to zj. So this is a line bundle on the nth power of C. But we actually can do even better, because so far we have to add this symmetric or antisymmetric condition. This is not something that is easily done in algebraic geometry. But actually we can instead take the nth symmetric power. Symmetric power. And this is still, and this is a smooth, this is a smooth complex manifold. Smooth complex manifold of dimension n. So why is it smooth? It is easy to see for n points on the plane. If you take n points in C, you can take the polynomial product of z minus zi, and the coefficients of this polynomial are coordinates on the space of on the symmetric power and symmetric power of C. If you take a polynomial, it determines the set of roots without the order. So
you're saying the bundle descends.
Yes, and symmetric sections are actually so there is a line bundle that I will denote with a thick L, and Laughlin states are exactly holomorphic sections of this line bundle. So it's the ideal situation. This is a more or less the push forward of this to symmetric power. So Laughlin states are exactly holomorphic sections of L.
So where is now the anti-symmetry versus symmetry? What happened with that?
So it's in the definition of this L. When you define this L, I mean it's not something you can do properly during a talk.
What is left is purely symmetric.
I see.
You divide out the antisymmetric.
Oh,
What is left is purely symmetric.
I see. Mm-hmm.
Okay, that's a little bit cheating but convincing. But that,
Cheating.
no, not really. It's a
But
this is true. I checked it in coordinates. It's really true.
You're now saying for this Laughlin state, the pole, the zero is at least of order b, but it can also be b plus 2 or B plus 10, it may
Yes,
happen.
it's allowed, yes, it's allowed. If you take two Laughlin states at random and you take a linear combination that kills the leading term, you will get a zero of higher order.
Yeah, okay.
So it's allowed.
In particular, all the Laughlin states for B plus 10, they are Laughlin states for B in your definition.
Yes.
Yeah, but there is a question of how many particles. So for n, d, b are just any.
No, right, just a question about definitions.
Principle, yes.
Okay.
Okay. I strategically, yeah. Okay. So let's do a summary. So we have the n-symmetric power of the surface times the space of fluxes. Actually, we have a line bundle over this whole product, because for every connection, any holomorphic structure on L, you can do this construction and you get a universal family. And then we project this to just the space of fluxes. So for each choice of L, right here we have L with a holomorphic structure. For each choice of L, we do this construction. We take the n-symmetric power of the surface, we take the line bundle, we obtain the space of Laughlin states. And what we obtain is a vector space. So for each point here, we have a vector space. So here we have a vector bundle, Laughlin bundle, Laughlin vector bundle. That is for every point, it's the space of sections of this L on the corresponding fiber. So again, if I denote this by pi, there is a notation in algebraic geometry for that. It's the analog of H0, but for families it's denoted with this R0. And what it means is that for every point you take the space of section, you take the corresponding fiber, and you take the space of sections. And this is the space of Laughlin states.
And for now, number of particles is not connected to the total flux at all. It's just
No, it could be arbitrary, yes. So there is a question of totally field space where the answers are much simpler, but so far they're independent.
And it's a vector bundle. I understand that the dimension may not jump, or may it? Is it like a bundle or a sheet?
So in this case, it will be a vector bundle, but in general, it's not. In general, it is a sheaf. But I will say it's analogous to this vanishing. There's a similar vanishing here.
How many terms?
Okay. And so now we are interested in. We want Chern classes of V. Maybe end rank. Of V.
Rank, I understand, but why do you actually want Chern classes? Or just we're curious?
So the first Chern class divided by the rank is the whole conductance.
Oh.
This is the Avron Zeiler write the argument. But there are also higher Chern classes. There are the second Chern class, the third Chern class, which are in principle measurable quantities that I think no one has measured, but maybe we're coming to that. Though I'm not prepared to discuss exactly what is the best way to measure them, but they are measurable quantities, and the thing is that you only see them in higher genus. In genus 1, you only see the rank and the first Chern class, so you see the degeneracy of the ground state, the whole conductance, and that's all there is. In genus 2, there is also the second Chern class, so there is something you can measure, but you have to do this more complicated picture Maybe there was a talk on Monday morning that I missed, where there were also 4 fluxes. So in principle, in this situation, you can also measure something else. So, so at least the first Chern class is an important consequence. The Grothendieck-Riemann-Roch gives all of them, so we can compute everything. And so one remark about, so Chern classes are topological invariants of a vector bundle. So that means that, well, there's always this question, how well do Laughlin states approximate reality? I don't know the answer, but I want to note that in this case, the first Chern class, the Chern classes are pretty robust. If you deform the Hamiltonian in any way, that does not change the degeneracy of the ground state. So you see, you deform the Hamiltonian, the space of ground states may move, but the topological invariants won't change. The eigenvalues of other states may change in any way, it doesn't change anything. The only problem is if another eigenstate comes down to the ground state and changes the dimension, then we have a problem. But if this doesn't happen, all these answers will remain the same. And the magic is that since Laughlin states are holomorphic sections, we can compute them using algebraic geometry. But the answer remains valid, even if we change the Hamiltonian to something that where the ground states are not holomorphic at all. Yes.
Next, if I have a genus 2 manifold and consider a single particle, the second Chern class is also quantized. Is that?
They all quantized.
So Chern classes are always integers.
Yeah. So is the second Chern class and the first Chern class, they're independent topological data or related?
Independent.
Independent. I see.
Yeah. So in some cases, for a totally field state, for instance, you can discover that there is a relation. But a priori, there are 2 different numbers that are unrelated.
You're saying that if I have a genus 2 manifold, even though my cognitivity is the same, but there still can be different phase distinguished by second Chern class.
Yes.
I'm still trying to understand what happens if n becomes very large.
If there are too many particles, then there are simply no sections of this line bundle. So this vector bundle becomes rank 0.
All right.
So in physics, that means that you have to put particles into high Landau levels. Exactly. In math, it means that it's just impossible to. There are no sections. Okay. So now I can write the Grothendieck-Riemann-Roch formula. The Grothendieck-Riemann-Roch formula computes the total Chern character of V. So the Chern character starts with the rank, then there's the first Chern class, and then there are higher Chern characters that can be expressed from Chern classes. They're actually equivalent to each other, but the Grothendieck-Riemann-Roch formula gives these. And it's the push forward under this phi of the exponential of the first Chern class of L times the tot class of the tangent vector bundle to the symmetric nth power of the surface.
Sorry, just a question on the logic. Did you say that the upper formula follows from the one below? You wrote 2 formulas for the same thing.
This is the definition of what is a Chern character of the vector bundle, and this is a formula that allows us to compute it.
So, can I ask one question?
Yes.
This push forward, does it mean integration over phi? Or
Yes, it means integration over phi, basically. So this is integration over the symmetric and symmetric power of C, and all these are cohomology classes. Cohomology classes on the product. So if you are not used to cohomology classes, you can think of them as closed forms, closed differential forms, and then you integrate those forms over the fibers.
Maybe you can explain, for me, the symbols one by one. The CH I understand. It's a problem with Swiss products. CH I understand.
CH I understand. Okay. So push forward is fine. So this is
including star.
So this is a cohomology class in big D, in the space of fluxes. It's a mixed degree cohomology class, so it starts with degree 0. In degree 0, it's just a number, which is the rank of the vector bundle. Then in degree 2, it's even degree. In degree 2, it's the first Chern class of the vector bundle. Then there's degree 4, degree 6, and so on. It goes up to degree 2G because this is of real dimension 2G.
And what is V is a bundle?
V is the Laughlin bundle, the bundle of Laughlin states.
Pi? Pi star.
Okay, so let's start with this. This is the hardest part to explain, but it's a complicated cohomology class on this product. So this is what the Grothendieck-Riemann formula tells us, and
TD is a Todd class?
TD is the Todd class that has its definition.
Yes. Are you going to explain what Todd class is?
So
I know.
If you ask me, I can. let me start by instead of defining the Todd class, I'll give you two examples. Okay, there's this power series. So it's 1 plus x over 2 plus 1/6 over 2 factorial x squared plus, minus 1/30 over 4 factorial x to the 4 plus and so on. And these things are Bernoulli numbers. So it's one of the mysteries of the algebraic geometry that Bernoulli numbers appear in the Grothendieck-Riemann-Roch formula. There are various explanations, but it's still quite surprising that you need these numbers to compute a push forward, to compute Chern characters of a vector bundle. And then, example, if you take CP, let's say R minus 1.
This is a generating function that you wrote for Bernoulli numbers, right?
This is just a generating function.
Not class. It's a generating function.
This is just
for
a power
Bernoulli numbers.
So far, it's just a power series. Okay, but now let's take a projective space, and let's take psi to be the so C1 of O of 1, or also the Fubini-Studi symplectic form. Studi symplectic form. Right, it's a two form that generates the cohomology of CP. Yeah. So then the Todd class of CPR minus 1 is this power series applied to psi to the power r. Right. So this is so I didn't truly give a definition, but there is a.
Sorry, just one thing.
Yes.
This seems to crucially rely on the fact that the whole cohomology is generated by just one form. Is that always the case?
In this example, no, it doesn't rely on that. It's not always the case, and there's a.
And you can generalize to it. Okay.
So, in general, if you have a line bundle, the Todd class of the line bundle is applying this power series to the first Chern class. If you have a direct sum of two line bundles, it's the product of these two things for the two line bundles. And then in general, when you have a vector bundle, it's not necessarily a sum of line bundles, but you can decompose it into line bundles by exact sequences. So there is a definition. in general, it is enough to think of a sum of line bundles. So the Todd class of L1 plus L2 is Todd series applied to C1 of L1 times Todd applied to C1 of L2. And with that, you already have a pretty good idea of what the Todd class of a general vector bundle is. And in this case, you apply it to the tangent vector bundle to this space.
And by the way, the fact that you have this series, I mean, ultimately you're only interested in the rank and the first Chern number. So in practice, you're going to Taylor expand the whole thing. Is that it?
So we have to expand this, push forward. We're interested in everything. We're not only interested in the first.
Sure, but like, sure.
We can. It's
If
not.
you want the whole conductance, you want the two first terms.
Yes. Yes. If you want the whole conductance, you need to. Exactly. Okay, so I was planning to tell you a little bit about the computation, but it is obviously too late. So I'll write the answer and just wave my hands a little bit. Okay, so first of all, the answer.
Answer to each question.
Yes.
Chern V. What is it?
Chern.
Ranks plus C1 plus.
One comment. Chern classes are integers.
Yes.
And whole conductance is fractional. So they're not equal,
So
but they're not equal, but they're related, right?
The whole conductance is this divided by this. They are both integers, but when you divide to integers, you can get a rational number.
Yes, but and we know this solution.
Paul, let's see the answer.
But what is the relation with other Chern classes? They do not have interpretation as a transport, do they?
Not so far, but
Therefore, there is no conductances, so you will talk about integers.
yes.
It's not about really fractional transport.
Let's move to the answer and then we will discuss what it means.
Let me write the answer. So it's so the mth Chern character, meaning the part of degree m, it's a sum for k varying from m to g. There are binomial coefficients. Choose g minus m, k minus m, n minus g plus p. So I will k minus g plus p. B to the power k minus m minus theta to the power m over m factorial. And if you have been following extremely carefully, there is one number I have to define that haven't been defined yet. So it's the number of quasi-holes. Number of quasi-holes.
And what is theta?
Okay, theta is the sum dxi dyi. So that's a closed to form or a two cohomology class.
G.
G. Yes, thank you. And the Chern characters are powers of theta. So if you take the Chern character number 0, this will give you the rank. It will be just a number. There will be no theta class, and you will get the rank of the vector bundle for m equals 0. For m equals 1, you will get the first Chern class. It is proportional to to the to theta. So it's this to form times the coefficient.
And is the degree of original bundle or of this capital or whatever, this L over this metric?
No, this is the Laughlin bundle. So it's the vector bundle of Laughlin states.
Through the surface. Flux.
Oh.
Degree of original bundle.
Okay.
See, they are related in this way. They are related in this way.
50 minutes. 50 minutes.
So I have to stop.
We'll have 10 minutes for questions.
Okay. So let's just look at this formula. So this is the first time you see the notion of a totally filled space. So a totally filled space is when there are no quasi-holes. So basically there are three cases: p smaller than 0, p equals 0, or p greater than 0. So p smaller than 0, it's the question that you asked. If there are too many particles, so the number of quasi-holes is negative, it means that there are too many particles. And then this will just give you 0, because these numbers will always be negative. And the convention is that the binomial coefficient is 0 when this is negative. So you will just get 0. For p equals 0, you see, you need k minus g to be non-negative. So the only term that will contribute is when k is equal to g. If I remove p, I have to have k equals g. So instead of this complicated sum, I will only have one term.
Yes.
And then if k is equal to g, that means this thing is equal to 1. This thing is also equal to 1. Something choose 0. So what I get is just b to the power k minus, b to the power g minus m. Minus theta to the power. So what I get is that the rank, let me write it here, for p equals 0. The rank is b to the power g. The first Chern class is b to the power g minus 1 times theta. So you get your fractional number. If you divide one by the other, you get 1 over b. Right, so this is the whole conductance. And then you can get the other ones there.
One quick question.
Yes.
How do you get a number out of theta? Theta is a 2 form, and you have a...
So on a torus...
If it's not a torus, precisely. So.
Yeah, if it's not a torus, then this is the answer. It's not a number. It's a number proportional times theta. There's no simpler way of saying it. It depends on which measuring devices you choose. If you choose two measuring devices that correspond to non-intersecting cycle, you will measure 0. There will be no hole conductance.
So you got like a family of integers.
Yes, but they are all. I mean, there's one master integer that is 1 over b, and all the others are contained in this theta, organized by theta.
So is it 1 over b times the intersection number?
Yes, exactly. Times the intersection index between the two cycles, where you're measuring the current and the difference of potentials. And then for p greater than 0, the formula was not known in general, so that's the answer is reasonably simple, especially if you look at the computation that led to it. The computation is much worse. I mean, this is much better than could have been expected from the computation. And okay, I think I'll stop here. Thank you very much.
People who do numerics always like to do calculations on the sphere. If we specialize all this to the sphere, then not much remains, right?
On the sphere, there is only the rank, yes,
Yep.
because there is no space of fluxes. So on the sphere, you can still. So you can take genus 0, and you will get. So you see, if you take genus 0, let's do the other case, the other extreme case. If you take g equals 0, then you have to take m equals 0, right? And then this thing will be 1, and this thing will be n minus p. Choose k k minus k plus, sorry, n plus p choose k plus p.
K0.
Okay, 0,
K
yes.
is
0.
k is 0, right. So n plus p choose p. Yeah. And this is times b to the power what? B to the power, so
0.
k is 0, b to the power 0. So that's the rank of the vector bundle, the dimension of the space of Laughlin states, and in genus 0 this formula was known.
Number of symmetric polynomials of degree.
Yeah. Yes.
So as you mentioned on the first day, we saw some double Corbiner geometry, and we even saw the picture, the photo of an experimental device.
Yes.
So but you said that maybe you can measure the second Chern class, but do you have more here? For instance, here it looks like in this completely field case, the second Chern class is completely slave to the first one, right? It's just a square of it. Okay, what are the thoughts? How can we, what can we extract from the second Chern class in addition to the intersection numbers?
So it's a question of interpretation. I don't know. Usually
mathematical interpretation. Suppose the first Chern class tells me the intersection matrix of my surface. Now the second Chern class, what does it?
Let me tell one thing. So they are always proportional to powers of theta, right? So this intersection index always play the same role. What differs is coefficients.
Yes.
And then there is one difference that you can spot. It's between projectively flat vector bundles and not projectively flat. So if V has a projectively flat connection, it imposes a restriction on its Chern classes that tells you that you can determine everything from the rank and the first Chern class. Then you will not find any new information.
Is it our case?
It's the case for the completely filled states. For completely filled states, you will not. Well, the prediction is that you will not find any new information. But if you have one quasi-hole, then you will find something different.
Yeah, last question.
Yeah, so I think my question is closely related. So if we consider integer quantum Hall effect Riemann surface with multiple geners, suppose I'm an experimentalist, I can probe the first Chern class by inserting flux and measure the current, which is effectively asking the linear response of current to electric field. So my question is, can I manipulate the flux to measure the second Chern class? Is there any ways to measure second Chern class by manipulating the current and the flux response? And whether second Chern class is related to the nonlinear response or others? So how to detect that?
So that's a very good question, and I'm not ready to answer. I think it's a little bit a miracle that the first Chern class is so easy to measure, and it's not as simple. I mean, there's this Zeiler, the Aaron, yeah.
So as you mentioned, the first Chern class and second, they're different topological data. So probably from this response point of view, is it possible that the nonlinear response is necessary in order to distinguish different topological phase at high genus?
What I suspect is that, so when you measure a current, you can measure the expectation value, but you can measure the whole distribution. And I suspect that you need the whole distribution to find the second Chern class.
But what you were saying before suggests that you need to turn on two fluxes, so it's in some way non-linear, but it's bilinear, right? You need to.
Yes.
Okay, if you call it non-linear, I don't know. It's linear in each of them.
Yeah, it's a
quadratic
influx. So
There's some measurement current correlations. According to the speaker on the first day who's left.
Okay, I suggest to thank the speaker.